Here's the discussion of the day. We have these two equations, and let me tell you, for the equation x is equal to x plus 1, this has absolutely no solutions, not even with complex numbers. And let me write that down right away. Absolutely no solutions. And please do not say infinity. I know infinity is equal to infinity plus 1, but infinity is not a number, unfortunately. So we don't look at infinity. But anyways though, why doesn't it have any solutions? Well, one way to see it is you can subtract x from both sides and we get 0 is equal to 1, which is a contradiction. Good. Or if you use the following argument. If you look at the graphs, firstly, we graph y is equal to x, which is this line right here. And secondly, we graph y is equal to x plus 1, which is going to be a parallel line to this one, but it has a different y-intercept. And you see, they are parallel, they do not intercept, so this right here should have no solutions. Now, here is the deal. For the second one, as you can see, I just changed this a little bit. I just put the square root for the x right here. Unfortunately, I cannot just subtract x from both sides and then get rid of the x or whatnot. And I'm just going to use the graphing argument. You will see right here. First, let me graph square root of x. It will look like this. And then I'm going to graph y is equal to x plus 1, which is going to look like this. I know the picture is not the best, so have a look right here. They do not intercept either. So are we going to say this equation has absolutely no solutions either? Well, not quite. We can say this equation has no real solutions because it does have complex solutions. And sometimes I'm just wondering, like, how do we know that if you look at the graph, do we have complex solutions or not? I know parallel situations, most likely it just has absolutely no solutions because you end up with a contradiction. That's usually the case for this to happen. But this and that, they are not like parallel like that. It's more like skew, but it's also not really like skew either because this is a curve, this is a line. Skew might not be a good term for it either, but they don't intercept, right? Another case I want to point out is, if you look at this equation, e to the x is equal to 0. If you graph e to the x, which is this, and if you graph 0, which is this, they do not intercept either. And this right here has absolutely no solutions either, just like the first one. So sometimes from the graph, I don't know if you can really see if it's a no solution or absolute no solution situation. Oh, yeah, and anyways, what I want to do for you guys is at least let me solve the complex solutions for you guys right here. And there are a lot more equations that I've done on the channel that you guys can go investigate, such as x to the x is equal to 0, or such as 0 to the x is equal to 2. But anyways, let's solve this right here. So for this equation, we don't really need to do anything fancy. First, I'm just going to square both sides so that we can get rid of the square root. So we get x is equal to, expand this, we get x squared plus 2 times this and that. So that's just 2x, and then plus 1 squared, which is just 1. And then I will just subtract x from both sides. Very nicely, we get a quadratic equation, x squared plus x plus 1, that's equal to 0. Then you see that we have a quadratic equation. The coefficient here is an odd number, it's just 1, so I will just use the quadratic formula. A is 1, B is 1, and C is 1. So we get x is equal to negative b, which is 1, plus or minus square root of b, which is 1, square, minus 4ac, 1 and 1 here, over 2a, and a is 1. Okay, so x is equal to, we have negative 1, plus or minus square root, that's 1, minus 4, which is negative 3, over 2 times 1, which is 2. We have a negative instead of the square root. We will get the I, right? So I'll put the I right here. X is equal to, in fact, not only we have a complex solutions, we actually have two complex solutions. First one, -1, plus the second one is the one with minus. And then the I, and then square root of 3, and then over 2. These are the complex solutions for this equation. If you plugging this into this x and x, work out the square root of a complex number, you will really see that it's equal to this complex number plus 1. In fact, these are the two complex roots of unity of a cubic. Two complex cube root of unity. So what I mean by that is, if you cube it, you actually will end up with 1. I thought that's pretty cool because if you start right here, if you subtract 1 from both sides, and if you factor it, you get x minus 1 times x squared plus x plus 1. The real cube root of unity of 1 is just 1 from here. And if you put this equal to 0, you pretty much solve that. But anyways, I do have a video on this, like if you want to do this with the quadratic formula, which we actually did it already. But if you want to use the Euler's method to solve it,